Our next talk is going to be presented by Lunjia Hu, and this talk is titled Towards Understanding Learning Representations, to what extent do different neural networks learn the same representation?
Thanks for the introduction. This is a joint work with Li Wei Wang, Jia Yuangu, Yue Wu, Zhiqiang Hu, Kun He, and John Hopcroft. Let me start with the motivation of this work. Deep nets work well partly because they are able to learn particular features or representations in their intermediate layers. And people have designed architectures in order to learn these representations better. For example, convolutional neural networks are designed to learn image representations well. However, there is a lack of theory on what these representations really are. There is one fundamental question that hasn't been answered. Are the representations learned by deep nets robust? In other words, are the learned representations commonly shared across multiple deep nets trained on the same task? In particular, suppose we have two deep nets with the same architecture trained on the same training data, but from different initializations. Given a set of test examples, we want to ask whether the two deep nets share similarity in their output of layer I. This question is trivial when layer I is the input layer because the similarity is high for both deep nets take the same test examples as input. When layer I is the final output layer, the similarity is also high, assuming both deep nets have tiny test error. So the real interesting question is how similar are intermediate layers, and do some groups of neurons in an intermediate layer learn features or representations that both deep nets share in common? And how large are these groups? In this work, we give a characterization of two groups of neurons learning the same representation. Let's look at these two neural networks. They have the same architecture, trained on the same training data, but from different initializations. We will focus on layer I and layer I+1. Let's look at these two groups of neurons. We say they learn the same representation if there exist linear transformations, A and B, that transforms the output of these two groups of neurons back and forth. To see why this definition makes sense, let's rewrite these two groups of neurons in this way, in this form of linear transformation. And we notice that each neuron in layer I+1 takes the inner product of the output of layer I and the weights. So we can move the linear transformation to the weights by adding a transpose. And if we do so for each neuron in layer I+1, we get two new neural networks where these two groups of neurons are swapped, but they still calculate the same functions. Therefore, in terms of functionality, these two groups of neurons are equivalent. And in this case, we say they are learning the same representation, or they form an exact match. Our definition for exact match also works for convolutional layers. We just need to replace the output of the neurons by feature maps and replace the weights by convolutional filters. So this definition has an equivalent form. That is, the output of these two groups of neurons span the same linear subspace. Formally, suppose we have test examples A1 up to AD, and we say the output of a neuron X on these test examples form a vector called the activation vector. If the activation vectors of two groups of neurons span the same linear subspace, we say the two groups of neurons form an exact match. And if the activation vector for every neuron in each group is epsilon close to the linear subspace spanned by the other group, we say the two groups form an epsilon approximate match. Under our definition, matches are closed under union, so there is a unique maximum match. And we define simple matches to be matches that are not the union of smaller matches. And we can show that any match is a union of simple matches. We also design algorithms for finding the maximum match and the simple matches to conduct experiments. So in our experiments, we plotted this figure showing the size of maximum match divided by the number of neurons for different layers. As you can see in this figure, we found few matches in intermediate layers, which suggests low similarity in intermediate layers. If you want to know more, come to poster number 26. Thank you.